The next question is based on the Gram-schmidt theorem, the Gram-schmidt orthogonalization procedure. So let us look at what the Gram-schmidt theorem says. The Gram-schmidt theorem. So the Gram-schmidt theorem says that given a linearly independent basis, we can form linear combinations of the basis vectors to obtain an orthonormal basis. So this is the Gram-schmidt theorem. So it says that if we have basis vectors which are not orthonormal to each other, then we can actually form an orthonormal basis using those basis vectors and certain combinations of those basis vectors. So what is the procedure? How do we do it? So there are certain steps that we need to follow to obtain such an orthonormal basis. So the first step is descale the first vector by its own length. So this rescaling will give us a unit vector. Note that we want to get orthonormal basis. On orthonormal basis, each of the basis vectors are orthogonal to each other pairwise, as well as each of the basis vector has a unit magnitude. So to get unit magnitude, we need to do this rescaling by its own length. So this is the first step. So take any one vector from the given basis vectors and then rescale it by its own length. The next step is subtract from second vector its projection along the first. So this subtraction will leave behind only the part which is perpendicular meaning orthogonal, perpendicular to the first. So this is the second step. Now what do? The third step. Rescale. Again we need to rescale, because remember we want orthonormal basis, that means unit magnitude. So rescale the left over from step 2, leftover piece from step 2 by its own length. Again, this gives us a unit vector. So let us see what this procedure is doing. So in the first step, we are taking one vector, then we are normalizing that vector by its norm or by its length. Then we are taking the second vector and subtracting its position along the first. So this subtraction leaves behind only the part which is orthogonal to the first vector. Then after that subtraction, whatever stuff is left, we are taking that vector and rescaling or normalizing it. So this is the third step, and then we repeat this procedure over and over for all the other vectors. Say for example, then we will take the third vector and subtract its position along the first and the second vector. So this step we will continue, and what do we continue? We take certain vectors, take let's say some nth vector from the basis, then subtract its projection along all the previous n-1 vectors, and then normalize the remaining part. So this is the procedure. In this procedure, we take any given set of linearly independent basis vectors and then obtain a set of orthonormal basis vectors. So to start off with, our basis vectors need not be orthonormal. If they are already orthonormal, then we already have the orthonormal basis. But if we have a certain basis vector set which are not orthonormal, then with this procedure we can obtain the orthonormal set. So this is the basic structure of the Gram-schmidt theorem. Now let us write this procedure in the Dirac notation. So remember, we have been writing down vectors in the Dirac notation. Dirac notation meaning we use kets to denote vectors. We are using the kets to denote vectors like this. So let us rewrite this procedure in the Dirac notation. So in the Dirac notation, let us say we have the following set of vectors. So this following set is a linearly independent basis vectors. So the first vector of the orthonormal basis that we would get is going to be first vector is just taking the first vector and normalizing it by its length. So we denote the norm or the length of a vector in this way. So this is nothing but the length of the vector, the norm of the vector. So this we obtain, from this we obtain the first vector. Then is this first vector really of unit magnitude? Yes, indeed, because if you take its projection on itself, if you find out this, the length of this vector, then what do you get? You get this, and this clearly is equal to 1. So this means that we have a unit vector. Now for the second vector, what were we supposed to do? See, the process says subtract from second vector its projection along the first. So we need to take the second vector. So for the second vector, what do we have? We take the second vector and then subtract its projection along the first. So we are taking its projection along the first. So this is the projection along the first. We are taking the projection along the first vector and subtracting it from the second vector. Now what do we need to do? We need to see, just to check whether this second this subtraction indeed gives us a vector which is orthogonal to the first one or not. So for that, let us just see the projection of this new subtracted stuff along the first one. So this is nothing but 1. So this is the same thing as this. So we indeed get 0. That means this new vector that we have formed is orthogonal. Now to make it orthonormal, we simply need to divide it by its norm. So the orthonormal basis vector over here would be simply this vector divided by its norm. So this will give us the second vector to get the orthonormal basis. Now for the third one, what do? We were supposed to continue this process, that is, take the nth vector from the basis and subtract its position along all the previous n-1 vectors and normalize it. So let us see. So we will take this vector, we will take the third vector, then subtract its projection along the first one, and then subtract its projection along the second one, So see, we have taken the third vector, subtracted its projection along first, this projection along first, this one is projection along second, and this is the third vector. So we have subtracted the projections along each of the previous remaining vectors. Note that this is the orthogonal, here I have made a mistake in the notation. This is taking projections, so like this we will denote. So note that we are subtracting the projections along the orthonormal vectors, right? This is not this 1 and 2 in the normal numeric format is not the original basis vectors we had. The original were 1 and 2 in the Roman, written in the Roman style. So we are subtracting the projections from this 1 and 2, the numeric style, which we had formed by using the Gram-schmidt process. So we need to subtract the projection along the first and the second vectors which we have formed in the orthonormal basis. So here in this process, when I've written continue by subtracting the projection along the previous n minus 1 vectors, this n minus 1 vectors are the orthonormal ones which we have already formed. So the third vector would then be, what do? The next process is to normalize it. So we will take the vector and divide it by its length. So this is how we will get the orthonormal basis. Now you see what is our orthonormal basis. In this, our orthonormal basis is given by this 1, 2, all this written in the numeric format, and then so on. So we will have 4 and so on until n being the dimension. So if we have n linearly independent basis vectors, so this is how we will obtain the orthonormal basis. So our orthonormal basis is 1, 2, 3 written in numeric format and so on. So this is the Gram-schmidt procedure for obtaining orthonormal basis vectors from a given set of linearly independent basis vectors which need not be orthonormal to start with. Orthonormal meaning each of the basis vectors are orthogonal to every other basis vector taken pairwise, as well as so orthonormal means orthogonal as well as it being of unit magnitude. So this is the Gram-schmidt process. Now let us look at the question that we have. So the question says, exercise 1.3.1, this says form an orthonormal basis in 2 dimensions starting with A equal to 3 I cap plus 4 j cap and B equal to 2 I cap minus 6 j cap. Then it says, can you generate another orthonormal basis starting with these 2 vectors? If so, produce another. So we have been given 2 vectors in a 2-dimensional basis vectors we have. So we need to orthonormalize it, that is use the Gram-schmidt process and obtain a set of orthonormal bases. So let us try and solve this using the procedure that we have. But before that, let us see if A and B are orthogonal to start with or not. So A dot B will be 3 I cap plus 4 j cap dot with 2I cap minus 6j cap. This is nothing but 3 into 2 is 6 minus 4 into 6 24. So this is not equal to 0, so which implies this is not orthogonal. So these basis vectors are not orthogonal. Are these A and B vectors indeed forming a basis for 2 dimensions? That we can see. Is A parallel to B? The answer is no. A is not parallel to B, because for vectors in 2D to be parallel, A and B need to be scalar multiples of each other. Clearly, 3I cap plus 4j cap is not a scalar multiple of 2I cap minus 6j cap. So it is not parallel to B. So they are indeed forming a basis for 2D, but they are a non-orthogonal basis, and we need to make an orthonormal basis. So what does our procedure say? See, our procedure said take the first vector and rescale by its own length. So let us take the first vector. So first vector here will be A. Take A and rescale it by its own length. So we will get the first vector of the orthonormal basis by taking A and rescaling it by its length. So what does that give us? That gives us 3I cap plus 4j cap divided by the magnitude. So that is 3 squared plus 4 squared. Sorry, I wrote 4 squared. This is nothing but 3I cap plus 4j cap over 5. So this is the first orthonormal basis vector that we have. Is it of unit magnitude? Yes, indeed. You can find out the magnitude. The magnitude of this vector would be 3 squared by 5 squared plus 4 squared by 5 squared, which is nothing but equal to 1. So this is the first vector. The second vector, to get the second vector, what did our procedure say? Our procedure said subtract from second vector its projection along the first, leaving behind only the part which is perpendicular to the first. So we need to take the second vector and subtract its projection along the first. So let us take the second vector. So we take the second vector B, and then what do? We subtract the projection of B along the first vector. So this is what we are going to do. So how do we do that? Take the second vector. Second vector is 2I cap minus 6j cap, and then we need to subtract. So this is the first orthonormal vector, and then we will take the projection of B along this. So that is going to be dot with okay. So this is projection of B along the first orthonormal basis vector. So let us try to simplify this. Just simple arithmetic. So we have 6 by 5 minus 24 by 5. So what we have here is 6 by 5 minus 24 by 5. So 6 minus 24 is nothing but minus 18. So minus 18, and then we have 5 over here and 5 over here, so that makes it 25. 5 into 5. So let us solve it further. So 18 into 3 is 54. So we have, let us take 1 by 25 common, and 18 into 3 is 54. We have minus sign over here, so this minus sign with this minus sign will make a plus sign. And then 18 into 4 is 72. Now let's take this 1 by 25 as a common denominator. So what we get, let's take 1 by 25 common, then what we have is 50 I cap minus 150 j cap plus 54 I cap plus 72 j cap. This is, simplify, 50 plus 54, that gives us 104 I cap, and 72 minus 150 gives minus 78 j cap. So this is the second vector, and we need to then orthonormalize it, means we need to make it a unit vector by dividing it by its own length. So the second vector will be this vector that we have divided by its length. So length of this vector, length of this is going to be nothing but 104 by 25 whole squared plus 78 over 25 whole squared. So this is nothing but this is the length. I do not want to find out the square root. This arithmetic you can do by calculator. Okay, let us see in the calculator. Let me bring my calculator. So this is square root of 104 squared is this number. (78) squared is this. So taking the sum, So square root of this is 130. So this is the length of this second vector that we have. We can simplify this. So simplify this 5. So this is nothing but 26 over 5. This is the length, and then so our final vector is going to be this divided by the length. So this divided by 26 by 5. So this is divided by 26 into 5, and 26 into 5 is 130. So we have this is the second vector. So what do we have for the orthonormal basis? So we have the first vector. First vector is 3i cap plus 4j cap over 5, and the second vector is this. So this is the orthonormal basis that we have obtained. This is the orthonormal basis that we have obtained, starting with the vectors a and b. These vectors a and b, which were clearly not orthonormal. So starting with two vectors in two dimensions which were not orthonormal, we have finally obtained these two vectors 1 and 2 which are orthonormal. So are they indeed orthonormal? Well, yes, because they are having unit magnitude and they are orthogonal to each other. We can check that once again. So we can check that once again. Let us see whether they are orthogonal or not. So we'll take the dot product of 1 and 2. This is going to be so we need to take this dot product. 104 into 3 is 312, and 78 into 4 is also 312. So this is equal to 0, which implies they are orthogonal. Then the magnitude of 1 is nothing but 3 squared by 5, it's 3 by 5 squared plus 4 by 5 squared. This is nothing but 5 squared by 5 squared, which is equal to 1. The magnitude, so this is a unit vector. the magnitude of the second one is so we had seen this 104 squared plus 78 squared over here 104 squared plus 78 squared we found this thing, and then when we took the square root of this, we had got 130. So that means 10 squared plus 78 squared is nothing but 130 squared. The calculator verifies it, so we get equal to 1. That means this is also a unit vector. So yes, indeed, these vectors 1 and 2 are of unit magnitude and they are orthogonal to each other. So indeed, they are forming an orthonormal basis in 2 dimensions. So this completes the first part of the question. Then we come to the second part of the question. The second part of the question said, can you generate another orthonormal basis starting with these 2 vectors? So yes, indeed, we can generate another orthonormal basis vectors. And how can we do that? Remember that we used the vector A as our first vector and normalized it by its length. But we could have also taken the vector B as our first vector in the Gram-schmidt process. So if we take the vector B as our first vector and normalize that and start with B and then take the projection of A along B and subtract it. So if we do that, if we take B as the first and A as the second, that is going to give us the second set of orthonormal bases. Let us see how we will get that. So if we take, so this is the second part. So now if we take B as our first vector, so then we need to normalize it. So dividing it by the magnitude, so magnitude of this is going to be two squared plus 6 squared, the square root of that. So 6 is 2 into 3, so that's what we have written. So this is our new first vector, which has unit magnitude. So we can, just to check, we can see that indeed this is equal to this is indeed equal to 1, so it is having unit magnitude. Next, we are going to take the second vector, which is A now. So we will take A and then take its projection along the first vector obtained from B. So see over here, in this we had taken A as the first vector and B was the second vector. So now just in this we need to replace this B by A. So this is what we have, taking the second vector and subtracting its projection along the first vector. So let us see what this is. Dot product with A. So this is our second vector, which is A, and then we are taking this projection of A along the first orthonormal vector that we have obtained from B along the direction of the first orthonormal vector obtained from B. So let us then evaluate this. This is just plain simple arithmetic. I'm just simplifying it. So 6 minus 24 is minus 18, and this minus sign makes it plus 18. So let's take this 20 as the common denominator. This gives us 60 plus 18 is 78. 80 minus 54 is 26. We can simplify this a little bit further. So this is what we get. Now we need to orthonormalize it, means normalize it by its length. So we are going to find out the length. (39 squared) (13 squared) So this square root comes out to be some numbers which are not integers, so we will leave it at that. So our second vector is So this is our second vector. So we have obtained another set of orthonormal basis vectors 1 and 2. I will rewrite them again over here. So our second set of orthonormal basis vectors are 1 equal to this is the second set of orthonormal basis vectors that we have obtained. Again, we can check whether they are indeed orthonormal or not. So let us do a quick check. The magnitude of 1 is the magnitude of the first vector the dot product of the first vector we are taking this is 1, so it is of unit magnitude, the first vector. For the second vector, again we will take its dot product with itself. and this 39 squared plus 13 squared we had seen over here. So this was giving us 1690. So this is also of unit magnitude. And are they orthogonal? Let us check that. Dot product of the first with the second. So this dot product, let us see, what does it give us? 39 into 2 is 78 minus 13 into 6 is also 78. This is equal to 0. So the dot product of the vectors are 0, meaning they are orthogonal. So we have a set of two vectors which are orthogonal to each other, and these two vectors are having unit magnitude. So these two vectors are forming an orthonormal basis in 2 dimensions. So we have solved this question. Now the interesting aspect to note from this question is, if we let us go up to the question. So the interesting aspect to note from this question is that using this Gram-schmidt process, we do not obtain a unique set of orthonormal bases. So the basis that we obtain from this Gram-schmidt process is not unique. So we do get an orthonormal basis, but this is not unique. We can get different sets of orthonormal basis vectors if we, depending on which vector we take as the starting point, which is that first vector that we take and rescale it to get a normalized vector. So it depends on the choice of the first vector. So in this question we had two vectors A and B. When we took A as the first vector, as the choice of our first vector, and normalized it, we got one set of vectors. When we took B as the choice of our first vector and normalized it, we got another set of basis vectors which were orthonormal. So we get different sets of orthonormal basis vectors depending on what is our choice of the first vector. So this Gram-schmidt process does indeed give you an orthonormal basis, but this basis is not going to be unique basis. And we saw that we have obtained two sets of basis vectors. So two sets of orthonormal basis vectors. This being the first set, this is the orthonormal basis, first set, and this below over here is another orthonormal basis vectors, the second set. So this solves this question. We have seen a new process in this question, the Gram-schmidt orthogonalization process, which gives us a set of Gram-schmidt orthonormalization process, which gives us a set of orthonormal basis vectors from any general given set of linearly independent basis vectors.